Applications of exponents and logs, day 2. We're going to explore a few other formulas and practice using those on the following examples. So we're going to start with a very simple exponential decay equation, and we'll go ahead and determine how many of these cells are remaining after the time allotted. So if we start with 100,000 cells and half of them are decreasing every minute, we can write that simple formula to be 100,000 times the decay raised to the power of t. And that will give us a final amount. And we'll call that amount y. In order to determine the number of cells after 10 minutes, we're just going to go ahead and put 10 in for t, and we get y equals 97.656. How long is it going to take the population to get to 10 cells? Well, that means my final amount turns into 10. My initial amount begins at 100,000, and I'm going to solve for t. Remember, we're trying to get this conglomerate of numbers by themselves, so we're going to divide both sides by that 100,000. And that gives us 1 over 10,000 equals 1/2 to the t power. Now we're going to make that switch. There's our base of 1/2. And we get log base of 1/2 with the argument of 1/10,000th, and that is going to equal the time. So we're going to use a change of base formula, or if you have that ability in your calculator, go ahead and type it in, and t is going to be approximately 13.288 minutes. Alright, Margaret Madison estimates she's losing her dental equipment, or not losing it, but losing its value by 1/6 every year. We're going to write an equation that represents this information. Well, we're actually using a depreciation equation here, so what we're going to say is that the total amount, or the final amount, of her equipment is based on whatever the amount was initially, times 1 minus its rate of depreciation raised to the number of years that it is in fact being used. So now we'll use that equation there to figure out what we're doing. Our rate is 1/6. So the number that is going to go in here will be 5/6. So we need to know our total amount. If it cost 175,000 brand new, if it's losing 1/6 of its value every year, and it's going to be 5 years worth of depreciation. Once you solve that, you get A equals $70,328.58. We're going to determine how long it will take for the machine to be worth less than $30,000. So we're going to say 30,000 is our number that we want it to depreciate to. Alright, and then we're going to, if you want to be technical about it, you want the value to be less than $30,000. So then we're going to start with our 175,000. Same 5/6 value raised to the t power. Divide out 175,000 to the other side. Drop your zeros, and you get 30 over 175 which reduces because they're both 5 divisible by 5. So we get 6 over 35 equals 5/6. Switch it into log form, and we get log base 5 over 6 of the argument 6 over 35 equals t. Use your change of base formula, or if your calculator has that function, approximately 9.673 years, or more than 10 years. Okay, we're going to introduce your exponential growth or decay formula. Looks like this. We'll be using that in the following sets of examples. So we have a population of 75,000, and now we have a population of 200,000 25 years later. We note that this is exponential growth, and since it's exponential growth, we will go ahead and use that formula we just took notes on just a moment ago. Alright, we need to model the equation that estimates that population. So by plugging in everything we know, we're going to get what we need in order to solve this problem. Alright, so before we proceed, before we have our model equation, we have to find this value k. This value of k represents this constant growth that we're going to use in order to determine our population at any given time. So remember, we're trying to get this conglomerate of numbers by themselves so we can apply log properties to it in order to get this number out of the exponent. Dividing both sides by 200,000 is my first step. I get an estimated number of 2.67, repeating, actually that's not estimated, that'd be exact, equals e times raised to the 25k power. Now because this is e, we're going to use natural logs, so that's going to be the natural log of 2.67 equals 25k. Dividing both sides by 25 gives you your resulting formula. Now my growth rate is 0.0392 approximately. The model then becomes y equals n times e to the 0.0392 power times t, which is my time. I need this constant before I can move on. So now what I'm going to do is plug everything in that I know based on part B. So we're at 75,000 to begin with, multiplied by e raised to the 0.0392 times 40 power, because the number of years that have gone by from 1970 to 2010 is 40 years. The estimated population at that time, just type that into your calculator and you get 2,773,711. Alright, next we're going to introduce value appreciation and value depreciation. That was actually shown on example number 2 just a few minutes ago. I have written appreciation underneath the word, and then likewise depreciation formula underneath its counterpart word. So notice appreciation increases the value, depreciation reduces the value. That's how your difference occurs. Very simple, very straightforward, no big deal. Okay, so we're going to use the R appreciation formula here, and we get A equals P, which is 1,200 students, times 1 plus 0.015, and we're going to raise that to the 6th power because that's the total number of years that have gone by. Remember, your rate has to be in decimal form, not percent form. And then you simply type that into your calculator, and we get an approximated population of 1,312 students. We have a little bit left over, but with students, it's not very good to have parts of them. All right, in number 5, we are going to be using the depreciation formula because we are eliminating medicine from our body. So we're going to start with 120, 1 minus 0.15, and we want to know how many hours it will take for half of the medicine to be eliminated. So we're unsure about the time, but I do know what the final amount is going to be. The final amount is going to be 60, which is half of 120. Remember, I'm trying to get this conglomerate of numbers by itself because I need to get this t out of its exponent and into whole number form. Remember, the quirk of the problem is it always turns out to be what you're looking for when you divide that out. Equals 1 minus 0.15, which actually turns out to be 0.85 to the t power. Now we can make the switch. Log base 0.85 of 1/2 equals the time it will take, which is approximately 4.265 hours. Question number 6. I'm going to try to put it all together in this problem. I want you to read through it, find your constant, and then use that constant to estimate the age of the woolly mammoth in part B. Be ready in class tomorrow to discuss your findings and the way that you determined what your final solution was.